Imagine a machine so vast it could swallow a cathedral whole. A racetrack, not for cars, but for the tiniest particles in existence. Deep beneath the border of France and Switzerland lies this marvel, the Large Hadron Collider, or LHC. It's a 27-kilometer ring of powerful magnets and detectors, the most ambitious scientific instrument ever built. Its purpose? To answer the deepest questions. What is the universe made of? Why does anything exist at all? Thousands of scientists from over 100 countries collaborate here, united by curiosity and the drive to uncover the universe's secrets. The LHC is their lens, peering into the fabric of space-time. It's a modern cathedral, dedicated not to the divine, but to discovery. Here we confront nature's greatest mysteries, not by looking up, but by looking deep within. Everything, from stars to the chair you sit on, emerges from the dance of fundamental particles. The LHC lets us watch that dance up close. We are explorers, venturing into the quantum realm, where intuition fails and wonder begins. The LHC is our ship, navigating this strange territory. It hurls particles at near light speed, smashing them together to reveal the universe's building blocks. In the debris, we search for clues about reality itself. The quest is simple, yet the most complex ever undertaken. In searching for the universe's building blocks, we're also searching for a deeper understanding of ourselves. So what is the Large Hadron Collider? At its core, it's a particle accelerator, a giant circular slingshot for protons. Large refers to its 27-kilometer size, hadron to the family of particles it accelerates, and collider to what it does, smash protons together at nearly the speed of light. The goal? To create new, massive particles by converting energy into matter, as Einstein's E=mc2 predicts. Many of these particles existed only moments after the Big Bang and vanish instantly. The LHC is our factory for creating and studying them. Thousands of superconducting magnets, colder than deep space, guide the protons around the ring over 11,000 times per second. When the beams collide, they do so inside enormous detectors, multi-story high-speed cameras that capture the shrapnel of these collisions. These detectors record up to 1 billion collisions per second, sifting through mountains of data for the faintest hints of new physics. It's a marvel of engineering, pushing the limits of technology and human ingenuity. The LHC is not just a machine, it's a window into the universe's most fundamental secrets. Every collision is a chance to glimpse something never seen before. The LHC is, in a sense, a time machine, recreating conditions just a trillionth of a second after the Big Bang. Back then, the universe was a hot, dense soup of quarks and gluons, a quark-gluon plasma. By smashing protons together, the LHC generates a fleeting fireball of this primordial state. Studying it helps us understand how the universe cooled and formed the atoms that make up everything today. The energy of these collisions, measured in tera-electron volts, is concentrated into a space unimaginably small, mimicking the early universe. This lets new exotic particles spring into existence for a brief moment. By studying these miniature Big Bangs, we test our most fundamental theories. The Standard Model describes these particles and forces, but it's incomplete. The LHC pushes this model to its limits, searching for cracks that could reveal a deeper truth. In these cracks, we hope to find the next great leap in our understanding of the cosmos. For decades, the Standard Model couldn't explain why some particles have mass. In the 1960s, physicists like Peter Higgs proposed an invisible energy field, the Higgs field, filling all of space. Particles interacting with this field gain mass, like celebrities slowed by a crowd. The Higgs boson is the field's quantum signature, but for 50 years it was just a theory. The LHC was built to find it. Scientists searched not for the Higgs itself, but for the unique pattern of its decay. On July 4, 2012, after sifting through trillions of collisions, CERN announced the discovery of a new particle matching the Higgs boson. It had a mass of about 125 giga-electron volts, and behaved exactly as predicted. This was a monumental day for science. The discovery confirmed the Higgs field's existence and completed the Standard Model's picture. It was the missing piece in our understanding of why matter has mass. But it also opened new mysteries about the universe's deeper workings. The search for answers continues. The Higgs boson's discovery was the final confirmation of the Standard Model, a theory describing all known matter and forces. It proved our understanding of how particles acquire mass was correct, completing the puzzle of fundamental physics. The Standard Model now describes 12 matter particles, 4 force carriers, and the Higgs boson as the capstone. But the Higgs's mass, about 125 GeV, is puzzling. Quantum effects should make it much heavier unless new physics is at play. This suggests the universe is balanced on a knife's edge, hinting at undiscovered particles or forces. So, while the discovery was a triumph, it also opened new questions. Why is the Higgs mass what it is? Are there more Higgs bosons? Does the Higgs field play other cosmic roles? By studying the Higgs in detail, physicists search for tiny deviations, clues to physics beyond the Standard Model. The Higgs is both an answer and an invitation to explore deeper mysteries. With the Higgs found, the LHC's most exciting work began, hunting for phenomena beyond the Standard Model. Supersymmetry, or SUSY, proposes every known particle has a heavier superpartner, potentially solving the Higgs mass puzzle and providing a candidate for dark matter. The LHC also searches for extra dimensions as suggested by string theory, hidden spaces that might reveal themselves at high energies. Evidence could appear as particles vanishing into other dimensions or as microscopic black holes evaporating in a flash. The LHC is also a factory for antimatter, the mirror image of normal matter. The universe should contain equal amounts of matter and antimatter, yet we see only matter. By studying antimatter at the LHC, scientists search for subtle differences that might explain why we exist at all. Each experiment is a step into the unknown, chasing the ghosts of new physics. The hunt continues, with every collision a chance for discovery. Everything we see, stars, galaxies, ourselves, is just 5% of the universe. The rest is dark matter and dark energy, invisible and mysterious. The LHC is our best hope for uncovering the nature of dark matter. We know it's there from its gravitational effects, but we don't know what it's made of. The hope is that LHC collisions can create dark matter particles, which would escape detection but leave missing energy behind. Physicists look for collisions where energy and momentum don't add up, a sign of invisible particles. This search is incredibly challenging, requiring perfect understanding of all known processes. So far, no definitive evidence has been found, but the search continues with every new batch of data. Discovering dark matter would revolutionize physics and cosmology. It would prove the universe is far stranger and richer than we ever imagined. The LHC's scale has sparked controversy, from fears of black holes to debates over its multi-billion-euro cost. Scientists proved the machine is safe, pointing out that cosmic rays hit Earth with far more energy every day. The real question, is it worth the investment? Fundamental research drives future progress. CERN even invented the World Wide Web. The LHC pushes innovation in technology, medicine, and data science. It inspires new generations of scientists and engineers. Ultimately, it's about what we value, immediate returns, or the pursuit of knowledge and our place in the universe. The LHC is a symbol of humanity's quest to understand. The LHC's journey is far from over. It's being upgraded to the high-luminosity LHC, which will produce 10 times more data, allowing for even more precise measurements and new discoveries. More data means better chances to spot rare phenomena, tiny bumps and vast graphs of information. The upgraded LHC will probe the Higgs boson, supersymmetry, extra dimensions, and dark matter with unprecedented detail. Meanwhile, plans are underway for the future circular collider, an even larger machine capable of reaching energies 10 times higher. This relentless drive to build bigger machines is fueled by our deepest curiosity. We are explorers, always seeking what lies beyond the horizon. The LHC and its successors are our ships, sailing into the unknown. The journey is long, but the quest for understanding compels us